All right, welcome everybody. So we have been working with regression and fitting linear models to our data. And so I want to just explain what we mean by linear models and talk about how we can fit more general models that we probably don't consider linear using these same techniques. So when we're discussing linear models, the linearity that we're describing applies to the coefficients beta in our model. So we want to make sure that each of these betas occurs only to the first power. And we're not referring to the predictors in our model. So here is actually a quadratic formula. Y is going to depend on not just x, but also x squared. So we include a second order term here. But this is still a linear model. It's still linear in the betas. So we can express this equation. We'll take a look at an example in a second. We'll be able to express this as the same sort of matrix equation for a least squares problem. And so we'll be able to use the same normal equations to solve a system that looks like this. Other common models that we might use in regression might be models that include an interaction term. So what happens when x1 times x2 when we include both changes to x1 and x2 in a new term. This would also be considered a linear model because each of the coefficients occurs only to the first power. Other things that are commonly done to our models is we might transform some of the variables in our model. We could transform the response variable to a log, and this is what would be called a log level scale, in case you're curious. And oftentimes in regression, they use log, which might look like log base 10, but they actually mean natural log. So that's just something to be aware of. And in fact, that model that we were working with earlier with GDP per capita as the response variable, we could fit a better model to that data if we actually put a log scale on GDP per capita. But that's a whole other discussion. You also may see models where we transform both the response variable and the predictor variable. And this is still a linear model because these betas, we've got two of them, each of them occurs to the first power. So we can still set up a matrix equation where we have a column of betas in our model that we then want to solve for that column vector beta. So let's take a look at an example where we may not want to use a linear model, but maybe a quadratic model might be a better fit. All right, so now let's consider the following data set that we collect data that has five observations here, where we look at a couple of hitters in baseball. So if you're not a fan of baseball, I'll explain what these terms launch angle and the distance mean. The distance you're probably familiar with. Batter is up in baseball. Here's the batter. And they hit a ball. And when they initially hit the ball, it goes possibly up. I suppose it could go straight down. And this angle that it goes up by, this is what we're calling the launch angle. And so what we're saying here is that this value, this angle, has some effect on how far the baseball travels overall. And so any baseball fans out there might know that nowadays, all of these, they're collecting so much data from every single play that goes on that sports analytics is just a huge industry now. And so for this model that we want to set up based on this data, so these angles are being measured in degrees and these distances are being measured in feet. And what we can observe here is that a linear model might not make sense because as the angle is going up, the distance is going up and then it starts to come back down. And this is the type of behavior we don't observe in linear models. They just go always up or always down by a constant amount. But maybe a quadratic model might make sense because these graphs, these parabolas, they tend to look like this might be a better model. And if you think about it, there's kind of an optimal angle that you want to hit a ball. If you hit it and the angle is too small, then it's going to be a ground ball. It's not going to go very far. If you hit a really large launch angle, then you're going to just get a pop-up that also doesn't go very far. So if you hit the sweet spot, then the ball is going to travel really far. And so the idea here might be, well, if I'm doing some analytics, what might be the ideal launch angle for a player to hit the ball? So now our model has three regressors: beta 0, beta 1, and beta 2. Beta 0 is the intercept, beta 1 is the angle, so that's going to be values like 10, 24, 36, 58, and 63. And then we also have a variable which is the angle squared. So that's going to be like 10 squared, 24 squared, and so on. So now we just have a different model matrix that we need to work with, where we have three different coefficients, so we should have three different columns. This first column corresponds to the fact that I have a 1 in front of all of these intercept terms. This second column is the angles that we've observed, and now I add a third variable. So this is really going to be done no differently than how we did regression if I had two totally independent predictors. So I treat angle squared as its own predictor. So I take 100 and I square it. I take 24 and square it. So now I have a third column that consists of the values for the angles squared. And it's important to note here that this matrix X has three linearly independent columns. I didn't combine these by adding or subtracting combinations of one column to get the other. In this case, I multiplied each of these entries by a different value to get this column over here. We've got our column vector of observed values. These are the observed distances that the ball has traveled. And now we can solve this system for the column vector of betas. And now we're going to have three of them: beta 0, beta 1, and beta 2, by taking the product of x transpose and x, taking the inverse of that product, times x transpose times y. So I entered all of this information, this matrix X, what we call the model matrix, this vector of observed values, into the Colab notebook, which is linked below, so you can check these calculations. So I inputted X and Y, and then in one line was able to calculate that product. And what we see is that the beta values that give us the smallest error would have an intercept term of 6.6, an angle coefficient of 12.4, and a coefficient in front of the angle squared as minus 0.14. So this gives us the following model, that the predicted distance is equal to 6.6 plus 12.4 times the angle minus 0.14 times the angle squared. And then we can use this model, similar to how we've used previous models. So if I know that my launch angle is 40 degrees, then what is the predicted distance that the ball is going to travel, for example? And we could interpret this 6.6 as saying, if somebody hits a ball with a launch angle of 0 degrees, then that ball is expected to go 6.6 feet. Interpreting these coefficients is a little bit trickier, because I can't just say increasing the angle by 1 degree is going to increase the distance by 12.4 feet, because we also are going to have some negative contribution from this term if we increase the angle. So interpreting the slope and the coefficient in front of the square term is a little bit trickier in this case when we set up a quadratic model. And so the last thing I want to leave you with in this video thinking about is I kind of mentioned why a linear model might not make sense, because these values go up and then they go down, and that seems very quadratic-like. But maybe we should use a fourth degree term over here, or maybe we don't want to include an intercept term over here. So I'm going to take a look at one more model for this same data set and talk about how we can compare this model with a separate model that I'm going to come up with on a separate video.